So we've seen 4 different reaction mechanisms that all start with some sort of substrate with a leaving group on it, and then also a base or nucleophile. And we've seen that those overlap quite a bit. And so the question is, how do you tease out which one of those 4 mechanisms is most likely to occur so that you can figure out what the product is? Do you get an alkene or do you get a substitution product? And then what's that stereochemistry or regiochemistry going to look like? So the 2 main things that we want to look at are substitution of the alpha carbon, and then whether the reagent is a good base or good nucleophile. But things like solvent are also important. So substitution. This looks like it doesn't narrow things down very much, but it actually helps a lot. If you have a primary or actually a methyl group bonded to your leaving group, then you're going to most likely have an sn2 reaction. We'll see in a couple of slides. It's slightly, that depending on the circumstances, it's possible to have E2, but really you have to have a poor nucleophile to make that happen. sn2, if you have primary or methyl, is usually what we see. sn2 cannot happen if you have a tertiary substrate, but all of the other reactions, sn1, E1, and E2 can occur. So then let's look at the nucleophile. And the nucleophile, or base, I should say. And so if you have a strong nucleophile or strong base, these are those impatient reactants. They're just going to get in there and they're going to make the reaction happen. And so sn2 or E2 are those concerted reaction steps. And we really see, particularly this is important in favoring the E2 mechanism, where a strong base will just go in and drive the reaction forward quickly. So you can also have E1 and sn1 when you have the weak nucleophile and weak base. So that's this is sort of the opposite situation here. So when everything is weak, that nucleophile or that base isn't really going to do anything until the leaving group leaves. So the leaving group has to leave and forming the carbocation, then the base will come in, or then the nucleophile will come in. But the weak ones are very patient. They'll just wait for that carbocation to form. It turns out that it's actually pretty difficult to separate E1 and sn1 reaction mechanisms. Both of them have their rate determining step as the formation of the carbocation, so you really typically get a mixture of products. So looking then at these sort of mixes here, strong nucleophile but a weak base. If you have a strong nucleophile, that will favor substitution because substitution requires a nucleophile. On the other hand, strong base will favor E2 because elimination requires a base. And so in this case, we have an impatient base. It's one that isn't going to just sit around and wait. It will just go right in and make that reaction occur. So we can put all of this information on a flow chart, and I'll post this separately. You can get these online as well. I should have put the link on here. I'll link it to the module page. But this summarizes the same information. So if you're looking at your alkyl halide or your alkyl group bonded to whatever leaving group you have, if that alkyl group is just a methyl, in other words, a CH3, then you're going to get an SN2 reaction. You can't get an elimination reaction because there's only one carbon there. You can't form a double bond with just one carbon. So the only option is substitution, and the leaving group won't just leave like it does in SN1 because a methyl carbocation is really unstable. So with the primary alkyl halide, as I mentioned before, really the most likely scenario in most cases is that you're going to get SN2. The one type of exception to that is when you have, and we'll go back here, when you have a strong base, that is a weak nucleophile. And so the example they give is tert butoxide, which is sterically hindered. And so since it's sterically hindered, the SN2 reaction isn't going to happen, but E2 can happen. So it is possible to get an E2 reaction, but in most cases it will be SN2. So let's jump down now to tertiary because it's the secondary one that ends up being kind of the most complicated one. So if you have a tertiary substrate where your leaving group's on a tertiary carbon, SN2 cannot happen. So we can eliminate that one. Remember, we said that up here. So SN2 can't happen in that situation because of that steric hindrance. And if you have a weak base, then that weak base is just going to hang out. It's not going to do anything. And we're down here. And it's going to wait for that carbocation to form. But once it forms, then you can either get SN1 or E1. And like I said before, it's really hard to separate those two. You usually get a mixture of both products. However, if you have a strong base, remember, since this is tertiary, you can't get an SN2 reaction. So it's not going to, the only thing that it can really do is it's quite impatient and you will get that E2 reaction. Okay, so kind of the most complicated one in here is the secondary alkyl halide situation. And here, one of the things that could happen is you could have a weak base. And if you have a weak base, then you get into the substitution. And so the weak base isn't really doing anything. It's just kind of hanging out, waiting for life to happen, or actually waiting for the carbocation to form. Or if you have a protic solvent, or pardon me, if you have a polar solvent that is not protic, then you could also get an SN2 reaction, assuming it's a weak base, but it could be a weak or a strong nucleophile, and you could get that SN2 reaction. So if it's a strong base, then that's going to be an impatient base. It's just going to get in there. It's not going to act necessarily as a nucleophile, although it depends a little bit on the solvent. But if it's really basic and not nucleophilic, then you'll get that E2 reaction. And again, if you do have the protic solvent and you do have a weak base, then you're going to go ahead and get the carbocation forming, and then you can get SN1 or E1. So a whole lot of different things that can happen. I think it just kind of takes practice in walking through each of these steps. And I think that's a good place to end. I guess the final thing to note is that if at all possible, we like avoiding SN1 and E1 reactions. It's better to get E2 and SN2 because, as you can see, you can get E2 product, you can get SN2 product all by themselves and not mixed in with other products. So you can avoid mixtures, and you can also avoid rearrangements with the SN2 and the E2 mechanisms.